Hello, dear students. Let's start the part 3 and the last part of the game theory that is dedicated to formulation and solving by using linear programming. So, guys, as you saw before and based on the different relationships that we defined, we want to talk a little bit about how to formulate based on the linear programming examples. As you remember, guys, as we learned before, there are three different forms of the examples, okay? If it's in the mixed strategy, if it's 2 multiplied by 2, so it means that it's applying analytic method easily, and if it's 2 multiplied by n and m multiplied by 2 with this condition that m and n greater than or equal to 3, we need to apply graphical solution. And in the new part of this game theory, we want to consider some games with the form of m multiplied by n, again with the condition of m and n are greater than or equal to 3, okay? It means that they are no more dominated strategy to reduce the size of table. So we need to solve this example with linear programming. One important item, guys, although I told you that in the other parts we apply analytical method or graphical solution, but for the other ones as well, we can formulate and model these formulas as linear programming. But for sure, linear programming is something more complicated and need more steps. So if it's possible to apply some more simple solutions like graphic solution or analytical method, so it's better to use them. But I tell you, you can apply for 2 multiplied by 2 or 2 multiplied by n or m multiplied by 2 as well, linear programming. So again, I repeat, here we are talking about a model that is m multiplied by n, that m and n, both of them are greater than or equal to 3. Okay, so by applying the minimax theorem and using the definition of minimax and maximin, okay, we need to solve this example and the same idea, okay? It means that when we are talking about minimax or maximin, it means that we want to minimize the maximum of the loss of each of the players. As you remember, the nature of these two players are the same. The difference is only in this negative that we multiply, okay? So in one item, we want to maximize. In the other item, we want to minimize, okay? So as we saw in the definition of mixed strategies, okay, these expected payoff of each of these values is the summation of this Pij, that is that value, the coincidence of a strategy I from player 1 and a strategy J from player 2, multiplied by the probability of the strategy I of player 1 and a strategy Y J of the probability of a strategy J of player 2, that we show it with Yj. Okay? So based on those definitions of maximin and minimax, okay, these elements, these probabilities for player 1 and these probabilities are of player 2 should be defined something like this, okay? they should be greater than or equal of something, okay, because they should be greater than the value of this item maximum. And for this one should be something like this, okay, less than or equal to minimax, okay, what we calculated in our previous slides, okay. It's just some definitions to understand what we are talking. It's simply the same item defining in the other forms. The more important parts will happen in the next slide. So guys, now it's the time of formulating a table, a payoff table based on a linear programming, okay? Based on the linear programming formulation. As you remember, in linear programming formulation, we had the definition, okay, we had the definition of our objective function that was maximizing or minimizing. Here exactly is the same. Depends on the point of view, it should be maximizing or minimizing, okay? As you see here, in the point of view, from the point of view of the player one, we want to maximize the loss of the loss of the game. As we see in the next slide, for sure, when it's from the point of view of the player. Two is minimizing the loss of the players. So as we see here, guys, uh, from one side maximize and one side minimize, and we know these two players have the relationship. So we can conclude one important item that we learned in the last semester. What was that item? A duality, okay? So the formulation of player one is the dual of the player two, obviously, because both of them give us the same value of the game, okay? The same value of the game. As you see here, guys, besides, we need to define some uh, constraints for our linear programming, okay. These are the constraints of our elements of linear programming. And finally, as an obvious part, we know that the summation of the probabilities is equal to 1, okay. We know that all probabilities are greater than or equal to 0. As you remember, in graphical solution, we had one probability equal to 0, okay. So this equal that comes, okay, let me correct this equal that we have here can be the same concepts, okay. So to formulate these elements, as you see here, we have greater than or equal, okay. This greater than or equal is exactly the same item that we had in the previous slide, okay. So to formulate these elements, I repeat, this P11 is the coincidence of strategy 1 of player 1 and strategy 1 of player 2. This P21 is the coincidence of a strategy 2 of player 1 and strategy 1 of player 2 up to here, guys. That is PM1XM, okay. That is PM1, sorry, is the strategy of M of player 1 and strategy 1 of player 2. So guys, what is this xm plus 1 and this xm plus 1? Here, instead of writing our value of the game instead of using v, okay, I use xm1. If the player 1 has 5 strategies, okay, the value of the game is equal to x6. So this v is equal to xm1, depends on the number of the strategies of one player. The value of the game is xm plus 1. It's obvious we want to maximize this value, okay? As I told you, I want to win as much as possible, or in comparison between two losses, I want to lose minimum, okay? So I want to maximize this winning, okay? So all these constraints, this part, all these constraints should be greater than or equal to xm plus 1. As you see in the previous slide, these elements are maximins, okay? If we move them to the left hand side of the inequality, are greater than or equal to 0, okay? These constraints minus the value of the game greater than or equal to 0. So to formulate one payoff table based on a linear programming, you should follow this approach. In the next slide, we review one example. So guys, in this slide, we review the example of the variation tree that we had in the previous slides. Okay, so as you see here, guys, in this table, as we checked, there is no saddle point. It means that there is not a pure strategy for this game. So we need to apply mixed strategies. The next step is, if it's possible to reduce this size, that is 3 multiply by 3, or not. It is possible to reduce this size. How can I reduce this size? By applying dominated strategies. Okay, by applying dominated strategies. Just check, make a comparison between these two strategies 2 and 3 for player 1. As you see here, guys, all the elements for strategy 2, okay, all the elements for strategy 2 are better than elements of strategy 3. As you see here, 5 is better than 2, 4 is better than 3, and minus 3 is better than minus 4. Okay, so I can eliminate this table. What remains for us? A table of 2 multiplied by 3. Okay, a table of 2 multiplied by 3. I can write it here. 1 and 2, 1, 2, 3. Okay, so what are the elements? 0, minus 2, 2, 5, 4, minus 3. Okay, as you see here, guys, now this 3 by 3 has changed to a table to 2 by 3. As we reviewed before, I can apply directly a graphical solution to solve this example, okay? But as I told you, I also can apply a linear programming, okay, for these types of models as well, because linear programming is the most complete solution for all the types of models. Okay, so it can be used for this type of model. Okay, so I want to formulate this model. So What are the probabilities? I want to formulate from 2 points of views. X1, X2, X1, X2, Y1, Y2, and Y3. Okay? I want to formulate this formula first, this table, first from the point of view of the player 1. What should I do? Easily. The player 1 says, I want to maximize, I want to maximize what elements, the value. I told you here, I show this value as xm plus 1. What is m here? 2. So I want to maximize x3 because m is 2 here. I want to show the value of xm plus 1, 2 plus 1, x3. Subject 2, okay? As you remember, guys, I need to formulate this one based on this form. The value, sorry, P11, that is 0 multiplied by x1 plus 5 multiplied by x2 minus the value, because it's the element that comes from the other side of this inequality, greater than or equal to 0. The second constraint is minus 2 multiplied by x1 plus 4 multiplied by x2 minus x3, again the value of the game. And finally, I need to write the third one, 5 multiplied by x1 plus, sorry, 2 multiplied by x1 plus multiplying of minus 3 to x2 minus x3 greater than or equal to 0. And we know that x1 plus x2 are equal to 1. Okay? And from the other side, I want to know xi is greater than or equal to 0. Okay, guys? So simply, I just formulated the table based on linear programming from the point of view of the first player 1. Why maximize? Because we want to maximize the minimum of losses, okay? The maximum that we calculated before, okay? So now in this table, we want to formulate our example based on the definition of player 2 from the point of view of player 2. Okay, guys? Easily, it's again the same formula. As I told you before, the player 1 and player 2, the formulating of these two are dual of each other. Okay? So for sure, this is minimizing, again, because minimize of the maximum of loss that we learned before, the value, this element, again, like the previous one, is n plus 1. For example, if player 2 has 6 strategies, it is y1, y2, y3, y4, y5, y6, y6, and this one will be y7. I want to minimize y7 as a value, okay? Again, here this v is equal to yn plus 1, okay? So Now it's formulating the other side. It starts with P11Y1 plus P12Y2 until P1N Yn, this side less than or equal to Yn plus 1. Okay, so we want to have this relation less than or equal. Okay, so if I move this Yn plus 1 to the left hand side, we'll have some constraints more or less similar to the other one, with this difference. There we had greater than or equal, here we have less than or equal. Obviously, again, the probabilities of the strategies of player 2, the summation of these probabilities is equal to 1. In the next slides, I will review the same table before formulate from the point of view of player 2. So guys, let's see this table. Okay, the table, as we saw, this third strategy was a strategy that we could eliminate. Okay, so again, the size of table is 2 multiplied by 3. Okay, so in this side, I have the same table. Let me draw it again here. It's the same table. 1, 2, 1, 2, and 3. Okay, 3 different tables that are 0, right? 0 better, 0, 5, minus 2, and 4, and 2, and minus 3. So this time I want to formulate from the point of view of the player 2. Okay, so as I told you, and as you can see in the previous slide, this side, and based on the nature of player 2, I want to minimize the value. What is the value? I told you it's Yn plus 1. How many? What is n here? 3. So I want to minimize Y4. Okay, subject to what are the probabilities, the constraints easily is 0 multiplied by y1 minus or plus minus 2 multiplied by y2, okay, and plus 2 multiplied by y3 minus the value y4, this time less than or equal to 0. The other one is 5 multiplied by y1 plus 4 multiplied by y2 plus minus 3 multiplied by y3 minus y4, the value, again, less than or equal to 0. And do we have any other constraints? No. And we know the probabilities 2 plus 3 is equal to 1, while y1 or yj, it's better to say, is greater than or equal to 0. So this example and the previous one, as you see, they are dual of each other. Okay, so for sure both of them gives us the same result because the game only has one value. Okay, so a good news. In the exam, I don't ask you to solve this one by simplex, okay? So the only item that I ask you is formulating an example from the point of the view of player 1, that was the previous one, or the point of the view of the player 2, that is this slide, okay? and solve that. If you want to solve by simplex or by solver as a practice, you can do that, but I don't ask you to solve that. For me, formulation of these formulas from different point of view is enough. This slide is a conclusion what I told you before, okay? The two formulations of dual of each other, okay? We could guess this one because as I told you, the two players are the same with a difference of one minus. That implies optimal mix strategies for both players can be found by solving only one linear programming problem, okay? As we saw in the graphical solution, because graphical solution is something like this solution. By finding x's, we can find our y's, or vice versa. By finding y's, we could find x's. So this part, let's go to the next slide. Let's wrap up the concept of game theory, okay? As you remember in the first slide of the game theory, I told you there are different types of games, okay, that are more complicated that in comparison between with two-person zero-sum game that are, for example, two-person constant sum game, in-person game, non-zero sum game, non-cooperative and cooperative games, or infinite games, okay? That if you are interested, you can enter in them and you can work on these items even for your TFHS. And finally, a conclusion of this section. In this class, we learned that by game theory, we can address general problems and make a decision in a competitive environment, okay, between two players. Game theory provides a framework for formulating and analyzing simple problems. Okay, based on the different coincidences, we learn how to formulate and how to decide about the different formulations and make a decision based on those strategies. And the gap exists between what theory can handle and the complexity of most competitive situation just solved by game theory. Thank you very much for your attention and have a nice time.